In the previous lecture, we defined sheaves and we saw that the sheaf and that the sections of a vector bundle E over X form a sheaf. And we also saw, given two sheaves, S, S and T on a topological space X, to give a map of sheaves phi from S to T is equivalent to giving maps of sheaves phi sub I from S restricted to Ui to T restricted to Ui such that phi, so let me, sorry, it's phi I, such that phi I restricted to Ui intersection Uj agrees with phi j intersected with Ui intersection Uj. So this was left as an exercise. Here X is covered by open sets Ui. So in this lecture, we want to define a map of sheaves. D sub I from exterior I omega to exterior I plus 1 omega. So recall that X is a smooth manifold and omega to X is the cotangent bundle and we had seen that one has the bundles lambda I omega to X for I equal to 0, 1 up to n, where n is equal to dimension of X. For I equal to 0, the 0th exterior is simply the sheaf of functions. Is simply, I'm sorry, the trivial bundle. The trivial bundle. X cross C. So in the previous lecture, we had remarked the following. Let E over X be a vector bundle and suppose over the open set U E is trivial. Then there is okay, so let's assume, okay, then there is a trivialization. So let's say there is an isomorphism U cross Rn to E restricted to U. These are the projections. So the remark was that the ith exterior of E, or let's just take the tensor so when I take the bundle E restricted to U tensor R, this is isomorphic to U cross Rn tensor R. Similarly, sim R of E restricted to U is isomorphic to U cross sim R of Rn. Similarly, exterior R of E restricted to U is isomorphic to U cross exterior R of Rn. So to see this, note that suppose phi from V to W is a linear map of vector spaces, then we get a linear map phi tensor R from V tensor R to W tensor R. Similarly, and so let's say SR phi from SRV to SRW, and exterior R phi from exterior RV to exterior RW. And moreover, if from V to W I have phi, and from W to let's say T we have psi, then psi compose phi is equal to the Rth tensor product of that map is equal to psi tensor R compose phi tensor R. And similarly, SR of psi compose phi is equal to SR of psi compose, and exterior R of psi compose phi is equal to exterior R of psi compose exterior R of phi. So in particular, if V phi from V to W is an isomorphism, then the associated maps and exterior R phi are isomorphisms. So, and the map phi tensor R, so the maps SR phi and exterior R phi are induced from phi tensor R, and phi tensor R on pure tensors V1 tensor V2 tensor VR is obviously defined by phi of V1 tensor phi of V2 tensor phi of VR. So the details are left to the reader. So from this, right? So from this, it follows that if phi from E to F is a map of vector bundles over X, then we get maps of vector bundles E tensor R the Rth symmetric power and the Rth exterior power. Of vector bundles over X. So, and clearly, if phi is an isomorphism, then phi tensor R, SR phi, and exterior R phi are isomorphisms. So from this discussion, this will follow easily. So star follows from this discussion. Okay, so we had applied this discussion. We had applied this discussion to the cotangent bundle omega to X, where we took u, x1, x2 and so on, xn, to be a coordinate chart. Coordinate open set. Then there is a trivialization u cross Rn to omega restricted to u. So given by x comma lambda 1 up to lambda n is sent to x, or the cotangent vector. Okay, let me use p, not x. Summation I equal to 1 to n lambda I dxi at p. And when we apply, so using the previous discussion, using star, we see that a trivialization for exterior R omega restricted to u is given by right. So u cross exterior R of Rn. So this is p comma, let me say lambda I maps to summation lambda I dxi at p. So here I is a subset of 1, 2 up to n, and cardinality of I is equal to R. So in view of this, the sections gamma u, the smooth sections, we are only interested in smooth sections. Exterior R omega restricted to u is given by is of the type summation fi, cardinality of I is equal to R dxi, where fi from u to R is a smooth function. So with this background, so by abuse of notation, we shall denote the sheaf of sections of exterior R omega by exterior R omega. So that is, instead of writing gamma u exterior R omega restricted to u, we will write, or instead of writing sections of, we will write exterior R omega of u. So our aim of this lecture, as I had mentioned in the beginning of this lecture, is to define a map of sheaves. The ith differential from exterior I omega to exterior I plus 1. And so we will use the exercise. We will use the exercise mentioned in the beginning of the lecture. And define. And first define. Define maps T sub u from exterior I omega restricted to u to exterior I plus 1 omega restricted to u. And then check that. So here u is a coordinate open set. For coordinate open sets u x1 up to xn, and then check that these agree on intersections. So since we want D to be R linear. So R linear. So we know that the sections of ith exterior omega over u are of the type summation cardinality I is equal to R f sub I dx sub I, sorry, dxi. So recall that if I is equal to I1 strictly less than I2 strictly less than IR, then dx sub I is equal to dxi1 wedge dxi2 wedge IR. So since we want du to be linear, R linear, it suffices to define du of f sub I dxi and then extend linearly. So define d sub u of I equal to summation j equal to 1 to n df by dxj wedge dxi. So this definition holds for, so recall that to define a map of sheaves from S to T, we need to define, so let's say the map is phi, we need to define maps phi sub u for every open set u, such that the diagram commutes. So it is clear that T sub u satisfies this condition since, so instead of, let's say, instead of u, let's say v1 and v2, since we have used the notation u, v1 and this v2 for all v2 contained in v1 contained in u. Du satisfies this condition since exterior r omega is trivial. So what I want to say is, so let me get like this. If V contained in U is any open set, then clearly the sections gamma V comma exterior R omega are of the type summation phi dxi. Because since exterior R omega is trivial over U, it is obviously trivial over V. So or yeah, I mean, I don't want to say anything more about this. Being trivial implies is trivial, and the trivialization of U gives a trivialization of V. The trivialization over U gives a trivialization over V. So here the FIs here are smooth functions from V to R. So we could have defined du. So the point is exterior R omega of V to exterior R plus 1 omega of V by, yeah, so du on elements of this type is just defined to be summation j equal to 1 to n d f sub I by d. So okay, we don't need a index I over here now. My I is fixed. So this implies that T sub u is a map of sheaves So we need to check that all these maps glue, but before that, let us check some properties of T sub u. Suppose omega is a section over an open set V, which is contained in U, and omega prime is a section in V exterior S omega. So we have an R form and an S form. Then d of omega wedge omega prime satisfies d omega wedge omega prime plus minus 1 to the r omega wedge d omega prime. So let us check this. So again, by linearity of d, it suffices to check this when omega is equal to f dxi and omega prime is equal to g dxj. So here cardinality of I is equal to R and cardinality of J is equal to S. So then d of omega wedge omega prime is equal to d of fg times dxi wedge dxj. This is equal to, by the definition, j equal to 1. So let me write L equal to 1 to n d of fg by dxl, xl dxl wedge dxi wedge dxj. This is equal to summation L equal to 1 to n f dg by dxl plus g df by dxl to dxl I wedge dxj. Capital J. Now notice that dxl wedge dxi is equal to minus 1 to the power dxi wedge dxl. This is because by the definition of the exterior rth exterior, or by the definition of the multiplication in the exterior algebra, so dxl, let's write this out, this is dxi1 wedge dxir, which is equal to, so when I switch these two, I get minus of dxi1 wedge dxl wedge dxi2 wedge so on dxir. Now when I switch these two, I get this dxi1 wedge dxi2 wedge dxil wedge dxl wedge and so on up to dxi3, and when we, in the end, we will be left with dxi sorry, minus 1 to the power r dxi wedge dxl. So using this observation, we put into this equation here, and we get L equal to 1 to n f dg by dxl sorry okay, that's f dg by dxl wedge dxi wedge dxj plus summation g df by dxl dxl wedge dxi wedge dxj. But now this is equal to summation L equal to 1 to n minus 1 to the power r f dxi wedge dg by dxl into dxl wedge dxj plus L equal to 1 to r df by dxl wedge dxi wedge g dxj, and this is equal to what we wanted to prove, d omega wedge omega prime plus minus 1 to the r omega wedge d omega prime. So this completes the proof. So this completes the proof of this important equality. And the second thing we need to observe is that suppose omega belongs to gamma is a section of exterior R over V, then d of omega is 0. So let us check this. So again, by linearity, it suffices to check this for omega is equal to f dxi. So then d omega is equal to summation j equal to 1 to n df by dxj wedge dxi, and d of omega is equal to summation j equal to 1 to n summation L equal to 1 to n d square f by dxl dxj dxl wedge dxj wedge dxi. So when L equal to j, dx L wedge dxj is equal to dxl wedge dxl. This is 0. So then this above expression, we can write it as summation j strictly less than L d square f by dxl dxj dxl wedge dxj wedge dxi plus summation j strictly greater than L d square f by dxl dxj dxl wedge. So now in this term, we switch j and L, so we get this is summation j strictly less than L. The first term is d square f by dxl dxj dxl wedge dxj, and the second term is plus d square f by x and j have been switched, so this is dxj dxl dxj wedge dxl wedge dxi. But now notice that this term in the middle, that is equal to d square f by dxl dxj dxl wedge dxj minus d square f by dxj dxl dxl dxj wedge dxj. Since we have switched both these, we get a minus sign, and since these two are equal, this gets cancelled and we get 0. Okay, so having made these two observations, we will check that if u x1 xn and u prime y1 yn are two coordinate neighborhoods, open sets, then du and du prime agree on u intersection u prime. Once again, it suffices to check this on a form omega of the type f dxi. So we first compute du of omega and then write the result. In the coordinates y1 through yn. So du of f dxi is equal to summation j equal to 1 to n df by dxj dxj wedge dxi. So, and in the coordinates y1 through yn, this is j equal to 1 to n df by dxj L equal to 1 to n. So the dxj is how to write that, how to write it in terms of the yi's is something which we had done in the beginning of the course. So this is just dyj, I'm sorry, dxj wedge dy by dyl times dyl. Wedge, once again, L equal to 1 to n dxi1 by dyl dyl wedge, and so on. And finally, n dxir by dyl wedge dyl. And this term over here that is simply equal to df by dyl dyl. So we get this whole expression above is equal to j equal to 1 to n summation L equal to 1 to n dxi1 by dyl dyl wedge L equal to 1 to n dxir by dyl. So next, so this we have done the computation in one way. Next, we will write omega in the coordinates y1 through yn and apply du prime. So so when we write, so omega, so recall that omega is equal to f dxi1 wedge and so on up dxir. So let omega s be the form dxis written in the coordinates y1 through yn. So that's just equal to summation j equal to 1 to n dxis by dyj times dyj. So therefore omega, we can write it as f omega 1 wedge omega 2 wedge and so on, wedge omega r. Now d u prime omega is equal to d u prime of f omega 1 wedge omega 2 wedge and so on wedge omega r. This is equal to du prime f wedge omega 1 wedge omega 2 wedge omega r plus f into du prime of omega 1 wedge omega 2 wedge. So here we have used property 1. Applied property 1. So this property. This property. Okay, and since, but now, and we can apply property 1 on this expression also, but since each omega s is d u prime of a function xs, xi sub s, this implies d omega s is equal to d square of xi sub s is equal to 0. And again, this implies again by using property 1, we get the second term is 0. This term is 0. So this implies du prime of omega is equal to du prime of f wedge omega 1 wedge omega 2 wedge omega r. But now the definition of du prime f is summation L equal to 1 to n df by dyl and this, all these are summation L equal to 1 to n dxi1 by dyl h. So this expression, let me call it dagger, is equal to the expression, let me call this dagger, since this is equal to this, we get du and du prime agree on u intersection u prime. So of course, I mean, omega was in gamma v comma xdr omega, where v is contained in u intersection u prime. Thus we get a map of sheaves. All these glue to give a map of sheaves d from exterior r omega to exterior r plus 1 omega. So we will also denote this by d or d sub r, and such that dr plus 1 composed dr is 0. So this is something which we had checked, and that is property 2, because of property 2. In particular, since we have a map of sheaves, T induces a map of global sections. Thus we get a complex zero to gamma x, comma exterior 0 of omega is just the smooth functions, is the trivial bundle, and the sections of the trivial bundle are just smooth functions, omega. Exterior 1 is just the bundle itself, and we go all the way up to n omega, where n is equal to dimension of x. And after that we have 0. So this is d0, d1, d2, and so on. So since d square is equal to 0, this implies we get the cohomology groups. Hi x comma r, that's equal to kernel of di modulo image of di minus 1. So these are the cohomology groups of the smooth manifold. X with coefficients in R. So clearly, Hix is equal to 0 if I is an integer which is not in 0n. Also, suppose x is connected and f from x to r is a smooth function, so then df is equal to 0 if and only if f is equal to lambda for some lambda in R. So f is constant. So thus there is a natural map from R, it's an isomorphic to H0 XR. So what is H0 XR? So we have to look at so let's just do this a little bit more carefully. H0 XR is equal to kernel of D0 by image of t minus 1. But t minus 1 is equal to 0, so this is just equal to kernel of t0. But now gamma of x, okay, so instead of writing ox, let me just change this to omega 0. So gamma of 0 is just equal to sections of the trivial bundle. And this is just equal to smooth functions. And from what we just observed, d of f is equal to 0 if and only if f is equal to constant. So yeah, so this improves that. There's a natural map from R to H naught XR, and that's an isomorphism. So I leave this as an exercise. Suppose X is a disjoint union of, let's say, finitely many manifolds Xi. Each Xi is smooth, is a smooth manifold and connected. Well, I mean, X is a smooth manifold and it's a disjoint union of smooth connected manifolds. So convince yourself or show that gamma x exterior I omega is direct sum I equal to 1 to n gamma xi okay xj omega xj, and the differential is also equal to the direct sum of the differentials. And from this conclude that H naught x R is isomorphic to Rn. So we will end here.